In this section, we're going to be looking at tangent lines and derivatives. And so specifically, in this set of videos, we're going to be going through the following things. The first one is, what is a tangent line and why is it related to derivatives? And, separately, what the heck even is a derivative? We're going to be looking at how to calculate a derivative using the defining function of what a derivative is. So how do I actually use this expression to find a derivative? And then we also want to talk a little bit about under what circumstances do derivatives exist versus not exist. There are times when you will be dealing with a function at a particular point and it won't have a derivative. And so we want to talk about the times that arises. So in this first video, we're just going to focus on, aside from this overview, we're going to focus on that first point. What is a tangent line and why is it related to derivatives? So to have this discussion, I'm going to give you an example first. Let's say that we have a function, and I'm going to draw a graph here of our function. Let's say we have a function that does this. So it kind of, I don't know, it almost looks like maybe a weird squashy cubic function. I don't know. It starts on the left-hand side, curving up and over in a kind of a hill, and then it swoops down into a valley before curving up and off into the right. So there we've got our function. And let's say that this happened to represent, I don't know, profit when we make X number of items. Okay, how much profit can we expect to make? So in a case like that, one of the things that we might be interested in is how fast is our profit changing when we make a particular amount of products, like the rate of change of profit. And all that a derivative is, what a derivative represents, is it represents a rate of change of y with respect to x. So how fast is your y changing when your x changes? And if that sounds familiar, if it sounds a little bit like rise over run, right? Change in y is the rise, change in x is the run, and in the past we've used that in slope formulas. That's actually totally related to what the derivative is and how it works. And so if you were making that connection as I wrote this down, that makes perfect sense. So I'm going to hopefully tie all of these concepts together for you. The idea of a slope, a tangent line, and the derivative. So let's say on this function, I wanted to get a sense of, slope. What is my rate of change of y with respect to x? And let's say I want to know, actually, I'm going to use a different color here. Let's say I want to know the rate of change at this point right here. I'm going to call that x1. So right here, how quickly is this function changing? What is my slope? Well, slope is something that we can only calculate for straight lines. And you'll notice that at this point, the function going through that point, that's not a straight line. That's a curved, it's a curve. The function is curved right there. And so we actually can't get a slope from just that. So then what I might think about is, okay, well, what happens if I just pick 2 points nearby, right? Like maybe these, and draw a straight line through those and use the slope of that line as an approximation of this derivative, the rate of change of y with respect to x. Well, that would be pretty good, but as you can see, it's not exact because our point is actually a little bit below that line that I just drew. Okay, well, what if I move the points closer together? What if instead of those points, I used points even closer to my point of interest on the curve? And I drew a line through there. Okay, that's pretty good. What if I move even closer? I'm gonna run out of colors here pretty soon. So even closer on either side. And I draw a line through those. Okay, that's also pretty good, right? So all of these are pretty decent approximations, but none of them are exactly on that point. And that's where we get this idea of a tangent line. So I'm actually going to get rid of all these lines and points that I just drew. And then I will show you what the tangent line is and how it's created. So a tangent line, when we're looking at tangent lines, what we're looking at is specifically if I were to draw a straight line that only touches the curve that I'm interested in, my f of x, my profit curve, it's only going to touch it at that x1. That's a tangent line. Okay, so this line that I just drew, it's just skimming the curve right there. It's only contacting the curve at that one point, at the x1, f of x1 point, and not anywhere else. That is a tangent line. So it just barely touches the curve and then moves away, okay? Now, if I can find the slope of that tangent line, that is my derivative. Okay. Now, how do we move from this idea of drawing all of these different lines that we were drawing to getting just this one? How do we figure out what this one is, right? How do we figure out the magic tangent line that just touches our curve at that one and only one point? So here's the idea. If I were to draw a different line, one of those earlier lines like we drew, right, with a point on either side, like that. And so this, let's say, is my x value. And then this number that's over here, the second point that I've drawn, that's beyond the point that I'm interested in, we're going to call that x plus h, right? And this distance between the two would be h. I have moved from this point x some distance away from that x, and I have gotten this other point, okay? Now, if I let that h distance between those 2 points, if I let that start shrinking and shrinking and shrinking and bringing those 2 points, the x and the x plus h, closer and closer and closer together, eventually they're going to come and converge when there's no distance between those 2 points. When those 2 points become 1 point, that is going to be the point that I'm interested in. Okay? So, how do we do that? Well, let me erase some of this stuff down here so we have a little bit more room, and we'll talk about it. All right. So again, thinking about the fact that slope represents rise over run, I'm going to look at these 2 points that we had set up on either side of the point that we're interested in. Now, how do I find rise over run when I normally want to do it? Well, when we think about slope, how far did I rise to get from this first point to the second point? And how far did I run to get from this first point to the second point, right? And then we create the quotient of those. We divide them. We put the rise over the run, so the change in y over the change in x, and that gives us our slope. Cool. Okay, well, so what is my rise and my run? Well, your rise is your y values, right? Your change in y values. So what is my y value at this first point? Well, because the point there is x, my y value is f of x, whatever it happens to be. Similarly, at this point x plus h, if I were to plug that into my function to find the y value, I would get f of x plus h, right? Those are my two y values of those 2 points. Now, how do I find how much we rose? Well, we take the further up y value and subtract the lower down y value, right? F of x plus h minus f of x, and that's our rise. That's the change in y. Then if we look at the change in x, or the run part of slope, right? If we look at the run part, how do we figure that out? Well, I started at a value of x. I went to x plus h. How many units did I move over on the x-axis? Well, I moved h units over, right? So that is the slope of this line, the line between those 2 points. And we just decided that as we let those 2 points become closer and closer and closer together and eventually converge to a single point, that's what gives us this magical tangent line and therefore the derivative. And what would that represent here graphically? Well, if we're letting this h value, the distance between the x and the x plus h, if we're letting that shrink and shrink and shrink and shrink all the way down until we get to one single point, that would be the limit as h approaches 0, right? We are letting that distance between those 2 points become nothing. And this is the formula for the tangent line, and therefore also the formula for the derivative. And so in the next video, we'll actually take a look at how to apply this to compute derivatives.